presentation. All right, introduction to rate laws. Laws that we don't break, as opposed to societal laws. These scientific ones, we keep them going. All right. So again, yesterday we talked about things that reactions depend upon. Okay. They depend upon how frequently these collisions between the molecules occur. And the higher those collisions, the higher the reaction rate. That is why when you look at these reactions, they start off pretty fast and then they start to slow down because you're running out of reactants to collide together because they've turned into products now. That makes sense? So it has to have that sufficient energy. It's kind of, we talked about the markers and how if I can bring these two things together, but if I don't, do it with enough energy, it's not going to react. Okay. So the lid of the marker won't stay on. No, I lost it. Okay. I made it back up. We're good. All right, so they also have to be of the correct orientation. So again, we talked about the marker, and if I try to put the lid on like this, it's not going to work. I have to line them up and have them with the correct orientation and energy to make that reaction happen. Okay, so chemical reactions then can be significantly different speeds. For example, rust. It takes, thankfully, according to my truck, it takes a very long time for rust to act upon something, okay? As opposed to me lighting a match where it's just a second, split seconds, okay? Or explosions. Did you guys see that explosion in, I think it was Virginia?
Yeah.
That was crazy. They served a search warrant on some guy's house and, were knock, and then the whole thing just blew. And I mean, they said that you could feel it for miles. I think it was yesterday or the day before. I don't know what he did. He probably had it set up somehow, but they said that he died. I think he died. So
if he was in the house,
he died. If he was in the house, he's gone.
Yeah, if he went boom, I don't think he's alive.
They found human remains, but they haven't definitely identified him as the person. So
I mean, I'd rather it be him than an innocent bystander. Unfortunately.
Yeah. So. Anyway, so like I said, the reaction rates are going to slow down as we are depleting those reactants. Beer's law then can be used to determine a change in concentration for a colored solution. And this is this is the lab that Jacob is currently setting up for you. You are going to start out with something called crystal violet, which is a violet color. I know, shocking. And then you are going to react that with sodium hydroxide, and it's going to go through a reaction. Over time, that crystal violet is going to fade to clear, and you're going to you're going to have a thing running on your vernier Lager Pro, and it's going to be showing the change in the absorbance of the light. It'll absorb less light as that goes through because that pigment is going away. Okay. And then you'll graph that. And then from that, you'll be able to determine what reaction order it is. And we're going to talk about reaction orders here in just a second. Okay. So the basis for this then with these kinetics is this collision theory. Okay. And again, we have to they've got to come in contact, so they've got to collide. They have to have enough energy when they collide, which is called activation energy. That's kind of like me pushing the marker and the cap together, okay? The collision has the correct orientation, so we got to get it lined up right, okay? And it has to be on that specific site within that. So there's a lot of stuff that has to go on in order for a reaction to actually occur. I mean, when you think about all of these things. Yeah.
What do you mean by specific site?
So if I tried to put the marker together and I went like that, it's not going to work. Okay. So I have to have a specific site for this to go into.
So like similar to orientation.
Yeah. Yep. Okay. So it has to be able to click in the right spot. Make sense? Okay. So, but both of those things have to line up right. So if I have the lid here, but I have this guy pointed, or if I have the lid here and I have this guy, they both have to line up in the right spot. Okay.
How do you make them do that? Is that too much?
I don't know that you do. I think it just has to like happen.
Like by chance?
Yeah. Yeah. Which if you think about all of the stuff that has to, I mean, you've got these reactions happening in your body all the time. I mean, in nature all the time. All of this stuff just, it's like, it's just chance. It happens. I mean, it just,
So
it's
if
crazy.
it doesn't work, does that mean like you can just randomly die?
But your body has systems. You're fine. Don't go home and like get stressed out about it or anything. You're fine. You're young. You're good.
Yet.
Yeah. Okay. So again, if these things are not met, you're not going to have a reaction. We say that those collisions are unsuccessful. Okay. So rate of reaction. We talked yesterday about the fact that this could only be determined experimentally. You cannot look at an equation and be able to determine the rates. Okay. It has to be found experimentally. And this, yesterday you were asking me, I think, about the equation and whether you could just use this blanketly to be able to, no. And I'm going to get into the idea of this zero order within the next few days. And that's why I said what I said. Okay. So if we look at this, this is what the rate law is. Okay. Rate equals K. K is called a rate constant. And that'll be the same no matter what concentrations of these items you have. You've got your reactants and they're raised to a power. Those powers are called the rate law. Okay. So D for this equation is raised to the 0 power. That means that it is a 0 order with respect to D. If we change the molarity, the concentration of D, that is going to do nothing to the rate. It doesn't matter if I have a 0.1 molarity or a 5 molarity. It's irrelevant. This rate is going to be the same. Okay, and that's what a 0 order reaction means. Now C is right here, and notice that that is a 1. Okay, it's not a 2. We didn't go over and grab coefficients and bring them over. Okay, you have to determine this experimentally. This is a first order reaction. That's why they have a 1 up here. What that means is if the concentration of C is changed, the rate of the reaction will change. So if we double C, if C goes from 0.5 molar to 1 molar, so we've doubled it, our rate will double. It'll go twice as fast. So however you change this, if you quadruple this, this will quadruple. That is what a first order reaction is.
Are there like second order reactions?
Yeah, there's a second order. There are other ones, but that go higher. They're pretty rare. Okay. So we typically deal in 0, 1, and 2 for our orders for here. Now, I will tell you, you can have fractional orders. You will not have them in AP chemistry, but if you go on to higher level chem in college, I'm fairly certain you will run into them there. Okay. I want you to be aware that they exist, but you're not going to have to deal with them at this point in your life. That is a moment. Okay. Yeah.
Will it be negative exponents?
No.
Okay.
All right. If you want to know, so we've been saying that this is 0 order with respect to D and first order with respect to C. If you want to know the overall order for the entire equation or reaction, you add these exponents together. So this ends up being a first order reaction because 0 plus 1 is 1. Okay. Again, the coefficients have nothing to do with this, with these rate laws. And you can only do them experimentally. So you have to look at experimental data. Good morning.
Are you collecting this stuff for the Craig Cares?
Kelly is. Oh, Craig Cares. Craig Cares might be Worm, actually.
Okay.
I think that's Worm, actually. I gave her my sweatshirt.
Okay, I'll grab it.
Kelly's doing the raffle basket.
Yeah, I did that.
Okay. And Worm's doing the other. Well, welcome to my world. I'm checking in 190 kids. So
Does this AP come?
Yeah.
this is
Get fired up.
APM.
Let's go.
Yeah.
Come on.
It's first hour. We're talking reaction rate orders, reaction kinetics.
That's very fun. I made it to work today and realized I forgot my bag with my computer and my work keys. I do have my phone, which I
That's
don't
all
have
you really
anything on
need.
it,
That's
so-
all the kids need.
So at least
So
I can be on Facebook, I guess.
Yeah.
Facebook,
it's so funny. All right. So here, if we look at 0 order, so we need to talk about units, okay? Because even if you come up with the right answer for your K value, like they may have you calculating K. If you come up with the right answer for K, but you have the wrong units on it, they're going to mark it wrong. Okay? So we need to talk about how we can figure out what those answers are. Okay? So your K, if it's a 0 order reaction, it's just going to be molarity over time. So you're going to have some component of time here. Okay? Because it's a rate. It's something happening for a given period of time. If you are a first order reaction, it's 1 over time. If you are a second order reaction, it's 1 over molarity times time. Third order reaction, 1 over molarity squared times time. And so forth and so on. Okay. So here's some examples of rate laws that would be 0 order. First order. Second order. You could have 2 different options. So this would be a 1 plus 1 gives you a 2. This would be a third order where A is cubed. And then you've got a 1 plus a 2 gives you third order. Here are 3 different things at first order.
For like 0 order, would it always just be 1? Because like something to the.
It's actually, you typically will just write down rate equals K. You won't even bother writing this stuff down. Okay? But they're trying to show you kind of what's happening in this diagram. But yeah, if it's a 0 order, you just write down rate equals K, walk away. Because anything that is to the 0 order is 1. That makes sense? So 1 times K would be K. So just write K. Okay. Okay. All right. So when we compare these, this is what we have to do. We have to look at the variable and how it's changing, and then what effect that's having. Okay. So if we change N, so we're changing our concentration, and there's no change to the rate, then that means that our reaction order is 0. If we change N and the rate changes by the same amount, so if we double N and our rate doubles, that's a first order. If our rate changes and the effect on the rate is squared, then that is second order. And then if the rate is cubed, that's going to be third order. Now, typically there's not reactions that go beyond this, because when you get into those reactions where it's above 3, it's not going to end up with the right kind of alignment. You're not going to have like all of those conditions that we talked about in the beginning. It's going to be very difficult to have all of those met in order for that reaction to proceed. So typically you won't see reaction orders greater than 3, just because of that. It's like too many things that have to come together on a perfect day to make it happen, and it just doesn't. Okay. All right, so here we have some data. We're going to look at our data. Now, when you do this and you're trying to figure it out for the different things, what you have to do, okay, everybody's with me, you're paying attention, right? This is a big one. You have to find a spot where the one thing here, so we're going to be looking at A. Okay, are you going to let me write on here? Why are you not letting me write? God, I hate this thing. All right, I'm just going to have to point then. So when you are looking at A here, okay, and we're trying to figure out the rate order of A. What did I do?
When you move your mouse on the bottom there's
Oh.
something that looks like a paintbrush. If you click it, does it work now?
It'll work for my mouse, but it's not working for this thing. Okay, but I can draw with the mouse at least. It's going to be crude, but I can draw with my mouse. All right. So if I'm trying to figure out the rate law or the rate order for A, the first thing I have to do is actually look at B. Okay. What I have to do is I have to look at B, and I have to find a spot where B isn't changing. Because I want to keep B the same so I can see what the effect of A is. So for A, I'm going to compare this guy right here and this guy right here to one another. So I went up by 3 here, didn't I? 1 to 3. I'm going to go over and I'm going to look and see what the rate is here. 1 to 3. What happened to this value? Yep. So did it change the same as here? So I multiply this by 3, right? Okay. A is tripled. Okay. And the rate went up here by 9. Yeah. Because if I take this divided by this, that's 9. So what happened to that 3? Squared. So that means that is a second order with respect to A. Remember, if we go back to this chart here, right? if this went up by 3, okay, yeah, so 3 times, and I do 3 squared, that equals 9. That's what happened in this reaction. Make sense? Good. Okay. So that means if that was squared, then that is a second order reaction. So B is going to be, when I go to do my rate law, I'm going to have, where's my mouse? Oh, this is so frustrating. I don't understand why all of a sudden I can't write on this stupid board. Okay. So the rate in or with B is going to be to the second order when we write that rate, or not B, I'm sorry, that's not right. A is going to be a 2 up here. Okay. Now we're going to go back and we're going to do the same thing, but we're going to do it with A being held constant, and we're going to see what happens when B changes. Okay, so here A is held constant, B is doubled. What happened to my rate? It doubled. Okay, so this is what order reaction? First order. So this is going to be raised to a 1 here when we write our rate law. Yeah? No. So do you see, I had to find a spot where, because I'm looking at B now. I'm looking at B. I have to find a spot where A stays the same. And I look and see what B did. B doubled, and my rate doubled. So if I go back to this chart, if this went up by 2 times, this also went up by 2 times, they changed it the same amount, then that's first order. Okay. So what I can do when I want to figure out, this is my rate law. This is what that looks like. So K equals A squared, because we said that that was a second order reaction. And B raised to the 1, we just don't write the 1 out. Okay. So once we've discovered the rate law, then if we have this data, we can plug and chug. Okay. So I just pick a point. It doesn't matter which point you pick off of here for this guy. Just whichever one you pick, make sure you're picking the concentrations at the same time that are the same, for that time, for that rate. Does that make sense? So they just happen to grab the first one here. So then they're going to, that becomes your rate, equals K is what we're solving for. Then they took the concentration here and plugged it in, and they have to square that, although 1 squared is 1. And then they put this guy in, okay? And then they just went through and did the algebra. All right? And then your units down here for K are 1 over molarity squared seconds. Remember we talked about units. If it's a second order reaction, no, it's a third order reaction, sorry. Then it's 1 over molarity squared times the time, whatever the time is. In this case, it happened to be seconds. My overall reaction order here is third order because I take the 2 plus the 1, and that gives me a third order. All right, I'm gonna try to see if I pull out of here. If I pull off of here. There we go. I'm gonna see if this will let me use my ink this way. Cross your fingers. Nope. Heck, piece of junk. Every day. Just a challenge every flippin' day with this thing. All right. Put another one here. So we are trying to figure out if more than one variable changes, then it's a little trickier to determine by inspection. You can compare 2 experiments like this. Okay. So here we've got these 2 held constant, right? So we can figure out A, but B doesn't, or I'm sorry, we've got B held constant, but we don't have a spot where A was held constant. Okay. So you can go through and you can figure this out by doing experiment 2 divided by experiment 1, keep the rates here, and then you can plug in your information here and solve for these coefficients. I've never seen anything this complex on an AP exam. Again, you can go. Okay. But it's possible. Okay. They go through all the fancy math for all of that. 2 raised to the m, yeah. So, yeah, that's ugly. All right, so let's look at one that's less ugly here. So we have a spot here where this guy is held constant. Okay. My A has quadrupled here. So it's gone up by a factor of 4. Everybody sees that? This is 4 times difference between these 2. Yes? What has happened to my rate? Did it increase by 4? Yeah? Then this is a first order with respect to the CO. All right? Now I'm going to find a spot where A stays the same. So A is staying the same here. Here, this guy did what? Doubled. So this went up by 2 times. This went up by, what happened to this guy here?
2.
Yep, he went up by 2 times. Okay, because remember, this is actually 0.0168, and this is 0.008. Piece of junk, I hate you. 84. That's a sad 4. It's a sad day. Okay. So this guy doubled. Can you see that doubled now that I pulled it out of scientific notation? Think of this as 8 and this is 16. Is that better? Well, okay. So if this doubled and this doubled, this is what reaction rate? 1. Okay. So what is it with respect to CO? 1. What is it with respect to NO3? 1. What is the overall reaction order? What do we have to do? Add them together. So it is 2. The rate law is rate equals K. I'm going to do my square brackets, which means molarity, concentration, good, okay? And then this will be our CO here. And this guy will be NO3. And I don't need to write my ones up there, they're just understood. Okay, now we need to figure out our value of K, because this is where you're going to lose points if you're not very careful. Okay, this is a second order reaction, so this is going to be 1 over what? What do we say for second order reactions? Yep, right here. So second order reaction, 1 over M, and then whatever our time is.
Do we have to memorize?
So how do you write that? Like,
How do I write this?
yeah, like an example of like a final answer.
Okay. So my K will be 1 over M. And then what is my time? Seconds. Times seconds. Piece of junk. Okay. So if I was solving for K, if I was trying to figure out, and we could solve for K here if we have, I do not have time. So we're on Bell's schedule. So whatever number I would get for K, followed by these units. So tonight you're going to do the was there a we do on there? Yeah, do the we do, watch the video, and then do the homework. You're going to have to sit down and play with these a little bit. Like this is going to take a little bit of practice. Once you get it though, it's going to be like, oh, this is easy. Okay?